Today we're going to do another activity, the basis of which is to find a relationship between two variables in the centripetal force equation that we've looked at for the last week or so. The procedure for this is fairly detailed. It's on page 245 and 246 of your textbook. Refer to that as you're doing the activity, but I'm going to summarize it for you here over the next few minutes. In the end, if you can remember the procedure just based on my description, that's okay. You don't need to go back to it. But if you have any questions, go back to 245, 246 for any details. And of course, you can ask me questions as you're doing it as well. What's the problem? What are we trying to accomplish today? Well, I told you we're trying to find a relationship. The problem is always phrased in the form of a question. So we're going to say that this problem is, what is the relationship between the radius of the path of an object in a circle and its speed? In other words, how does, if we got an object moving in a circle like this, okay, how does the speed of that object, how is the speed of that object related to the radius of the circle? Is it a linear relationship? In other words, if r goes up, does v go up? Is it an exponential relationship? As r goes up, then v goes up by a factor of v squared. Okay? Is it as r goes up, v goes down? What is the relationship between r and v? All right. We're trying to find the relationship between r and v, the radius of the path and the speed. Then what do you think we're going to change in this experiment? What's my manipulated variable? What is it that we are testing here? We're testing speed and radius, yes, but only one of them are we directly changing. Okay, we can only have one manipulated variable. We change it, and then the other one responds to that. Stephanie, which one are we changing? We're going to change the radius, yes. We're manipulating the radius of the path here, and then, of course, responding to that will be the speed of the object that's going around the circle. We got to keep everything else the same. Everything else the same. I'm not going to list for you the control variables. You're coming up with the control variables. Bottom line is, if speed is changing because the radius is changing, then whatever else you have here, whatever other variables that you could be dealing with here, aren't changing. So you can list a bunch of control variables here probably, okay? The procedure amounts to this. You're going to have an apparatus that looks like the one up on the board there right now. You got a tube, this plastic tube. It's actually a PVC tube that's cut down with a string threaded through that PVC tube. On one end of the string, that string, by the way, is not attached to the PVC tube. It's not tied to it whatsoever. It's free to move right through this PVC tube. On one end of this string is a rubber stopper. That rubber stopper, you're actually going to swing around. On the other end of the tube, or the other end of the string, I should say, is a 100-gram mass. Don't get those backwards. Okay, we want to swing around a rubber stopper using a 100-gram mass to pull it back. We don't want to swing around a 100-gram mass using a rubber stopper to pull it back. Why are we swinging around the rubber stopper as opposed to the 100-gram mass? Well, if something happens to go wrong here, and the string happens to break, or the knot happens to come undone, and something flies off and hits somebody, we'd prefer it to be a rubber stopper than a 100-gram mass. Okay, 100-gram steel masses hurt a little bit more than rubber stoppers. 100-gram mass tied on one end of it, and a rubber stopper tied onto the other end of it. Okay, here's what's going to happen. You're going to swing this thing around. You're going to find, because the string, the rubber stopper, and the mass are not attached to the PVC tube that's in the middle that you're holding on with your hand, you're going to find that the rubber stopper is going to, the faster you swing it, is going to go further out. And then you're going to find the slower you swing it, the rubber stopper is going to come back. In other words, there's going to be times when the 100-gram mass is pulling the system back to a smaller radius, and there's going to be times when the sheer speed at which you're swinging it produces a bigger radius. Within each trial, okay, and you're going to do a bunch of different trials here, but within each trial, you want to keep this radius right here constant. So how do you do that? Well, you're going to have to use some practice here. Okay, you're going to have to swing it around, swing it around, swing it around. Okay, as you notice the R is getting bigger, we'll slow it down. As you notice it getting smaller, then speed it up. you will, with a little bit of practice, manage to swing it around several times with the radius staying the same. You'll find the speed at which you have to swing it in order to keep the radius the same. Okay? It's going to take some practice. Do it. Manage to get the radius staying the same in that one trial. Okay, now what you got to do is measure the value of that radius. That's your manipulated variable, right? So measure that radius. You can't measure speed directly, even though that's your responding variable. What do you think you're going to measure to ultimately get speed? Any ideas? Yep. Yes, in the end, you're going to use 2 pi r over t to find the speed. So what is it you're going to measure, Gary? Not the frequency, but you're close. The period, yes. So ultimately, you're going to measure that radius. Let's say it's 10 centimeters, although we want to record that in meters. We'd say 0.10. You don't need to write that number down there because, of course, your numbers for radius are going to be whatever they are, right? Not going to be the same as my numbers. Then you're going to measure the period twice. But because this thing is going to be going pretty quickly in order to maintain the same radius, the period's actually going to be fairly small. I don't want you to measure the time that it takes the rubber stopper to go around the circle once. I want you to measure the time that it takes the rubber stopper to go around the circle 20 times. Let's say it takes you 40 seconds to go around 20 times. What would be the period? If it takes 40 seconds to go around 20 times, the period would be 2 seconds. You're not recording the period directly. You're recording the time that it takes to go around 20 times. And then you're repeating the experiment with the same radius. This time, maybe you get 41 seconds. Next, change the radius. This time, make it 0.2 meters or something. Okay, something different than 0.1 meters. Doesn't matter exactly what it is. Record the time that it takes for 20 revolutions again, and then 20 revolutions again. Okay, get 2 different times for this one, and so on and so on and so on. Fill in your data table. There's space in this table for 5 trials. Okay? I would like you, if you have time, to do more than 5 trials. Okay, 5 trials is pretty iffy for plotting a graph, which is ultimately what you're going to do here. So if you can, do more than 5 trials. Do upwards of 10 trials if you have time. But at a bare minimum, let's get 5 trials done. That's my data. Okay? That's what I'm collecting in the classroom here. Then it comes time for my analysis, which, by the way, these questions you can find on those pages of your textbook that are referred to at the beginning here. Radius again, I measured this, measured this, measured this. Okay, good. Now it comes time for actual calculations. Okay, I need to see this data table under data, and then I need to see this analysis table under analysis. The average time is going to be this time plus this time divided by 2. So we'll say T1 plus T2 divided by 2. For the first case, that would be 40.5 seconds, right? 40 plus 41 divided by 2 is 40 and a half. Now the period is that average time divided by 20. So 40.5 divided by 20 would be about 2 point something seconds. Now my speed, somebody said, I think it was Lewis earlier on, said we're going to use v is equal to 2 pi r over t to find the speed. 2 times pi times the radius divided by the period to get the speed. So get a number for that. What are you going to plot for your graph? Notice most of these tables we've already done here, right? Or sorry, most of these questions we've already done. Find the average time. Well, you don't need to answer this question separately because you've already done it within your table, right? Okay, this one. Find the period. Well, we've already done that in our table. Okay, find the speed. We've already done that in our table. Identify the controlled, but then the responding and manipulated variables. We've already done that way back at the beginning of our lab. The only questions that we need to do kind of separately that we haven't already done as part of our normal write-up, question 5 and 6. Identify the force that acts as a centripetal force. Determine its value. Okay, you're going to think about that as you're doing the activity. Right there. And then you're going to plot a graph of velocity. It actually should be speed versus radius. Speed versus radius. So your graph is going to look like this. Speed on the y-axis, radius on the x-axis. If you get a graph that looks like this, then you're going to say that as r increases, v increases linearly. In other words, it's a linear relationship. As one doubles, the other one's going to double. Okay, if it looks like this, well, then you'd say as r increases, v increases by a factor of v squared. If it looks like this, you'd say as r increases, the speed decreases, and so on, right? Whatever your graph tells you, that's going to be the relationship that you're trying to find, going back to your problem. Your conclusion actually relates to your hypothesis, when we have a hypothesis. And for this one, we are going to have a hypothesis. Remember how your hypothesis is phrased? You guys remember that? If the manipulated variable, this is not really conclusion, right? It's hypothesis. Conclusion just relates to that. If the manipulated variable, then responding variable. What's going to happen to the responding variable? So you might predict that if the manipulated variable increases, then the responding variable will decrease linearly. Or if the manipulated variable increases, the responding variable will, if the radius increases, then the speed will increase exponentially. If the radius increases, then the speed will increase linearly. Okay, whatever you think is going to happen, right? If blank happens to the manipulated variable, then blank is going to happen to the responding variable. And then your conclusion basically answers that, okay? Okay, so basically we're going to say in the conclusion, here's my hypothesis. If the radius increases, then the speed is going to increase linearly. This was proven because, and I know this because the graph of v versus r produced a straight line. Or this was disproven because the graph of v versus r produced a curved line. Or this is inconclusive because the graph of v versus r produced data points that are all over the place. Didn't produce any kind of recognizable pattern or whatever the case may be. So write your hypothesis way back near the beginning of the lab, and then basically, was your hypothesis right, and how do you know? That's what your conclusion is. Finally, your sources of error, along with suggestions for improvement, right? 2 or 3 good things that you could have fixed, and 2 or 3 good ways that you could have fixed it. So what do we got to hand in? What do we got to hand in for this puppy? We got problems, we get variables. Well, I've pretty much done those 2 for you already, except for the control variables. Your hypothesis. Remember, if the radius does what? If the radius increases, if the radius whatever, if the radius blank, then speed will blank. The speed's going to increase. The speed's going to decrease. The speed's going to increase linearly. It's going to increase exponentially. It's going to increase by a factor of v cubed, v to the 2 or whatever. Your data, which is your table. Your analysis, which is your table. Your graph. And the answer to 1 or 2 of those questions that you haven't already answered as part of your table or your graph. Your conclusion, which is relate that back to your hypothesis. Technically, what you're supposed to do here in the conclusion is restate the hypothesis, and then was it proven or not? And then, of course, your sources of error. You want to have 2 or 3 good sources of error with suggestions for improvement along with that. Your procedure, again, is in your textbook. Okay, if you forget how to do it, you can refer to those pages in your textbook, but you do not need to write it down as part of your lab right up here, okay? I don't need to see that. Okay, the procedure is pretty much word for word what we have in our textbook. Okay, there is no value, I don't think, and recopying that, just simply retyping something that's already given to you word for word. Got it?